In 1819, we learned of a discovery by Hans Christian Oersted. In 1819, we learned that electricity generates magnetism. There were no exceptions to that. Every time we had a moving electric charge, a magnetic field would be generated. That electric charge could be moving through the air as a single electron. It could be moving through a wire as an electric current. It could be ions moving through water or some other liquid or some other gas. Every single time moving charges existed, we generated a magnetic field. 12 years later, in 1831, there was a discovery made by two guys, independent of one another, one in the United States, one in England, Michael Faraday and Joseph Henry. They discovered what amounts to essentially the complement of Oersted's 1819 discovery. If electricity generates magnetism, then magnetism can generate electricity. So in 1819, we learned electricity generates magnetism. In 1831, we learned that magnetism is generated by electricity. Usually we use Faraday's name, but sometimes we mention Henry's name as well. Having said that, there's conditions attached to this one. Electricity always generates magnetism. Magnetism sometimes generates electricity. In order to generate electricity for magnetism, we have to have two things. One, we have to have a conductor. That's a wire, usually, something that conducts electricity. The other thing we have to have is a magnetic field, a conductor and a magnetic field. Something has to be done with those two things in order to cause electricity to be generated by magnetism. The first thing that you can do is move the conductor. You got a wire, you got a magnet, move the wire. The second thing that you can do is move the magnetic field. You got a wire, you got a magnet, move the magnet. Doesn't really matter which one you're moving. Okay, in the end, it's relative motion. If one moves relative to the other, it doesn't matter which one is actually moving. You ever find yourself sitting in a parking lot outside a store, your mom's gone into a store, you don't want to go into the store looking for groceries or whatever, and maybe you're kind of sitting in the seat and you kind of nod off a little bit, and then all of a sudden the car beside you starts backing out of the stall, and you feel like for just that second when you're kind of awakening, you feel like your car is going forward. You ever feel like that? You ever notice that? If you have, then you know that perception-wise, it doesn't make any difference which car is moving. Okay, one car is moving backwards or you're moving forward, it feels exactly the same. Okay, that's relative motion. Here, if you have a wire and a magnetic field, it doesn't matter which one's moving, it's the same effect. Just like it is with the car beside you moving or you moving, it's the exact same effect. So, you got a conductor, you got a magnetic field, you move one of them. You're going to generate an electric current in the wire or in the conductor. That's how most of the electricity that we use today is generated. That is on large scale, not in batteries. It's a different thing in batteries. That's a chemical reaction. But most of the electricity that's on the grid that comes to our houses through power lines is generated by conductor, magnetic field, move one of them, generate an electric current. Most of the power in Alberta is generated by burning coal. Well, we don't generate electricity directly by burning coal. What we do is generate heat by burning coal. And that heat boils water. And that boiling water turns into steam. And steam rises. And that steam rising turns a turbine. And that turbine consists of a bunch of really strong magnets. So now you got magnets moving. There's some wires over here. When you move a magnetic field relative to wires, then you're going to generate an electric current. Hydroelectric power, which they use a lot of in Ontario, works the same way, except it's water falling, which turns a turbine. Turbine is a bunch of magnets. Magnets moving relative to these wires off to the side generates a current in the wire. Even nuclear power, which they have in Ontario and New Brunswick, and lots of places in the United States and the rest of the world. Even nuclear power, okay, splitting the atom generates a ton of heat. That heat boils water, creates steam, rises, turns a turbine. What does a turbine consist of? Magnets. Now you get magnets moving relative to a wire, which generates an electric current in the wire. You got a wire, you got a magnetic field. You move one of them, you generate an electric current. Now, there is a third thing that can happen as well. But we're going to star the first two because those are the ones that we see in Physics 30. The third possibility is that you change the strength of the magnetic field. Make it stronger, make it weaker. You can still generate an electric current that way without moving one of them. But in Physics 30, we'll always see that one of them is moving. Either the magnetic field is moving or the conductor is moving as well. This is just kind of for future reference that this can happen. Lenz's law is an application of what we just learned with Faraday and what we learned near the beginning of this unit with Oersted. Lenz's law says this. Number one, when a magnetic field, B1 we'll call it, the first magnetic field, a magnet, in the demonstration that we just did, the magnet that we dropped through the copper tube, when a magnetic field and a conductor move relative to one another, it doesn't matter which one moves, right? I could drop the magnet, I could drop the copper tube. Doesn't make any difference. That we generate an electric current. So magnetic field number one generates an electric current. That was Faraday. Right? We learned just a few minutes ago that Faraday/Henry said that when you have a conductor and a magnetic field and you move either the conductor or the magnetic field, you're going to generate an electric current. That's what's happening right here. We've got a conductor, we got a magnetic field, we drop the magnet, so it was moving, that generates a current in the conductor. Now, it's a really, really weak current, okay, this current that's generated right here, a weak current, but a current nonetheless. Oersted said, and this was the discovery that was made in 1819, Oersted said that an electric current generates a magnetic field. So we've got magnetic field number one causing a current, and then we've got the current causing a second magnetic field. We'll call that B2, magnetic field number two. So magnetic field number one causes an electric current, which in turn causes magnetic field number two. Now you get two magnetic fields. There's the one that I dropped in the demonstration that we just did, and the one that was produced as a result of the electric current that was produced in the coil or in the copper tube. Now this is the crux of Lenz's law. Everything we've just done up here is not new, right? The first bullet is Faraday. The second bullet is Oersted. This is Lenz's law. Magnetic field number two, the one that was just produced by the current, will act together with magnetic field number one. That's the one that I dropped. Those will act together to oppose the motion. So in other words, if I drop the magnet and gravity's pulling it down, there's got to be a magnetic force that pushes it back up. And that's why it didn't fall as quickly as the piece of steel did, right? Because there was an opposing force pushing it up. If I pull a magnet to the right through a conductor, then there's got to be a magnetic force that acts to the left to oppose the motion. If I pull something upward, then there's got to be a magnetic force acting downward to oppose the motion. If I push something backward, then there's got to be a magnetic force forward that acts to oppose the motion. There's going to be two magnetic fields, the one we start with and the one that we create, and they will always act together to oppose the motion. Otherwise, it would violate the law of conservation of energy. Think about that. If I dropped a magnet and it sped up at a rate more than 9.81 because its motion wasn't opposed but rather helped, then we'd have more kinetic energy at the bottom than we had potential at the top. We would have created energy from nothing, and that can't happen. So if there's going to be a force, and there has to be a force because we have two magnetic fields, then it has to be a force to oppose motion rather than helping the motion. Let me give you a couple of practical applications of this, types of things that you could see in questions that illustrate or are illustrated by this new concept that we learned called the Lenz's Law. If you look at the back of the sheet that I handed out to you a few minutes ago, you see these two examples. I'll just work through these two examples with you. And then if we have time, we'll do one or two more. Here's a loop, a coil of wire. There's a light bulb attached to it. No battery this time. Does that light bulb light up right now? Why would it? There's no electric current flowing through the circuit. If you don't have an electric circuit, then you don't have a light bulb lighting up. Let's put a magnet nearby it. The magnet is set up so that we have a north pole on the left side and a south pole on the right side. We still don't have the light bulb lighting up. Remember what Faraday said? You got a conductor, you got a magnetic field. How do you generate a current? Yeah, if you move one of them. You could either move this coil or move this magnet. That will generate a current. Let's move the magnet to the left. If I move the magnet to the left, that generates a current, an electric current inside this coil. Or sorry, in this coil, in the wire in this coil. Which way does it go? I don't know. But that current will generate another magnetic field. Okay, remember, magnetic field number one will generate an electric current. Okay, that electric current will generate a second magnetic field. The second magnetic field will act with the first one to oppose the motion. So, if you want to oppose the motion of this magnet, what is the polarity of this induced magnetic field going to look like? What pole is this, south or north? It's got to be north. If it's moving this magnet to the left, the only way to oppose it is to have a north pole and push it back to the right. That's a north pole. This is a south pole. The magnetic field inside goes from south to north. We take our coil, right, this manipulative that we built here a couple weeks ago. We put our thumb in the direction of the magnetic field, which is to the right, put our fingers on the word front, and our fingers point up on the word front. So, looks like this. The blue magnetic field generated the green current. Even though we didn't know which way the current went, it still generated it. And that green current generated the red magnetic field, such that the red magnetic field acted with the blue one to oppose the motion. We just kind of worked backwards to see which way the current pointed, right? Blue magnetic field going to the left. We have to have a north pole right here to oppose that motion, which meant the magnetic field, the red magnetic field had to point to the right, which meant the current had to go clockwise. We'll do another example here, okay? I see a couple faces that are still a little puzzled. That's okay. We'll do a couple of more examples here. Here's the next example that's on the handout that you have. Here's your light bulb. It's not lighting up because we don't have a circuit. Here's a magnet with a north pole and a south pole. It's moving downward. How come it's moving downward? I dropped it. Gravity pulls it downward, right? Okay, I've got a magnet and I've got a conductor. When I move one of them, it generates a, remember Faraday, you got a magnet, you got a conductor. Move one of them, it generates a current. So we get a magnetic field number one, generating an electric current. Which way does that current go through this wire? I don't know. Clockwise, counterclockwise, I don't know. But there is a green current formed here. That current will form a second magnetic field that we'll call B2. We know that second magnetic field has to be such that it creates which pole right here? South pole and north pole. We have to oppose the motion. The only way to oppose the downward motion here is to pull it back up. Downward force of gravity, upward magnetic force to oppose that motion. So the only way to do that is to have a south pole against a north pole here to attract it. Magnetic field is upwards. Thumb in the direction of the magnetic field inside, which is up. Fingers are going to go to the left in the word front. So that means the electric current is going to go to the left in the word front, or on the front there. And it's going to go to the right in the back. So in other words, it's going to end up going counterclockwise there. So again, blue magnetic field produces green current. Which way does the current go? Don't know. That green current generates red magnetic field. We know which way the red magnetic field has to point because it has to oppose this motion. Therefore, we can figure out, using the coil rule, which way the green current points. Yeah, question?
Does that magnet have to be a permanent magnet?
This magnet right here?
Yeah.
No, actually, that's a good question. Does this blue magnet have to be a permanent magnet? No. As far as the solenoid up here goes, if there's a magnetic field that is moving relative to it, it can't distinguish between a permanent magnet and an electromagnet. So if you did have some kind of coil down here, this blue magnet was really a coil that was hooked up to a battery, it would work the same way. Okay, it wouldn't be a particularly efficient way of generating electricity because you'd be using electricity to generate a magnetic field, which would be used to generate electricity, which would mean you'd lose a whole bunch of energy in that process, but it would work, yeah. Okay, let's do another one. This one's not on that example sheet here, but we'll just do another one to help you out with it, and we've got a little bit of time here. So let's say we've got we'll leave it at that. We've got a light bulb here, same as we've had before. Let's say we've got that same situation almost as we had in the first diagram. A magnet to the right with a north pole and a south pole. Instead of pushing it to the left, we're pushing it to the right. Magnetic field number 1 creates what? An electric current. Okay? Because you got a wire and you got a magnetic field. And Faraday/Henry said, when you got a wire and you got a magnetic field, if you move one of them, you generate a current. We're moving the magnet, we're generating a current. That current generates what? We don't know which way this current goes, but we know that there's a current there. This current produces another magnetic field. That's Oersted, 1819. Now we get 2 magnetic fields. Which way is B2, by the way? Which pole is this? This is north, and this is south. If this blue magnet is moving to the right, if I put a north pole there, does that pull it back to the left to oppose its motion? Anna? No, it helps it along, right? That violates the law of conservation of energy because this thing is given a little bit of a push to the right, and now all of a sudden it's going to move even faster to the right because of this magnetic force. That can't happen. So we'd put a south pole right here. It was moving to the right. We have to pull it back to the left to oppose its motion. And the only way to do that is to attract it. Magnetic field pointed from south to north. Take our coil, put our thumb to the left, fingers in the direction of the current on the word front, point down. So it turns out that electric current is down in the front and up in the back. Try this one. This is similar to one that's on a practice question set that I won't bother having you do. I'll post it if you want to do it, I suppose, but I won't make you do it for homework, okay? Unless you're just looking for extra practice. We've got a magnet here that's actually, let's keep our color coding system here. We've got a magnet here that's falling because of gravity. We've got a ring here. Try to draw this here. You see what I'm doing there? Does it kind of make sense? It's like a ring that looks like this, but I've tried to draw it kind of three-dimensional. Whoops. A ring that looks like this with an opening in the front. Okay, does that make sense? Okay, it's copper, it's silver, it's aluminum, it's some kind of conductor, but it's not ferromagnetic. Okay? I want to know which end, A or B, becomes positively charged. Okay, when we drop this blue magnet nearby this conductor, what does the blue magnet do? Magnetic field number 1 does what? When you move a magnet nearby a wire or a conductor, it generates a current. So magnetic field number 1 generates a current, a green current in this copper loop here. Which way does the current go? Don't know. But we know that that current generates another magnetic field number 2. It's like a coil, right? A solenoid, except it's a very narrow one. What does that magnetic field look like? Well, if we pretended this was a bar magnet that was produced in this coil here, or in this loop, this end would have south or north? South? North? Who says south? Who says north? It would be a north. If it's falling, we have to push up on it to oppose its motion. And the only way to push up on it is to have a like pole there, north against north. Okay, so we now have a magnetic field inside this coil that goes from south to north. Stick a thumb up. Fingers go to the left on the word front. So it means the current is going to go this way. Which end becomes positive, A or B?
The electrons can't flow through this list, okay?
No, they won't flow through the opening. No. They'll go one way and collect at one end. So which end is positive, which end is negative? A is positive because the electrons flow away from it, and B is negative because the electrons collect at it. Does that make sense? Does that make sense? Real quickly, we will take a look at practice question set number 18. There's only 2 questions. First one says a magnet is dropped into an open copper tube as shown below. Well, that one that I just did wasn't like practice question set. It must have been like the assignment, because I know I did it with somebody earlier today. I was thinking it was a practice question set, but it must have been the assignment. Anna, you've done that? Or you've looked at it? Okay. Okay. So we're dropping this magnet. We're going to call this magnet number 1. Magnet number 1 generates what? Magnetic field generates electric current in this copper tube. That electric current in the copper tube, whichever way it goes, generates what? Second magnetic field. Second magnetic field must oppose the motion. So how do you oppose the motion of a magnet that's coming down North Pole first? Yeah, gravity's pulling it down. You got to push up on it. In order to push up on it, you have to repel it, which means north at the top and south at the bottom. Good. Magnetic field inside goes from south to north. Okay, thumb up. Fingers go to the left on the word front. So the electric current would go this way, to the left on the word front. It means the answer to this question is what? We want to know the magnetic polarity and the current. It's going to go A. Is it A there? Make sense? The follow-up question of that, and that's the last one we'll do on this, the physics principle that is used to explain the induced electron flow and the induced magnetic polarity is the conservation of what? Yes, conservation of energy. Because if it didn't oppose the motion, and that it's critical that we use that phenomenon of it opposing the motion. If it didn't oppose the motion, then it would violate the law of conservation of energy. So the answer is